Hi, this is the question we were asked to critique by Dermot. It's a question from Anderson's book, and it's based on surface geometries. So in this question, we're asked to develop the surface of a transition piece. It says we can either use triangulation or rebattement. The problem is we can't actually develop two of these surfaces because they're not flat surfaces, they're warped. Okay, so there's two hyperbolic paraboloids in this question. Okay, so we know that because if we're looking at parallel lines for true lengths and such as and like that, the baseline here of this surface and the baseline here are parallel, so that's okay. Parallel and parallel lines, that means they're true length, which is good. Now if we have a parallel line and a line that's not parallel to the xy line, then usually that means that's also a true length, but the true length is when it's not parallel. However, if both these lines are on the same surface, they must be parallel to be true length, okay? Or one of them, they must either be both parallel to the original line, or one line needs to be parallel on the surface and then the opposite line, both of them will appear skewed off to the side. So because of this, we can say that these two lines are skewed lines, okay? And any surface stretched between two skewed lines is a warped surface. So that's a warped surface, and it's called a hyperbolic paraboloid. So I'm first going to go on and explain how this is a hyperbolic paraboloid and how what Anderson has drawn in the book can't actually be correct. So first off, what I've done is I've gone and I've drawn exactly what Anderson has shown us in his book, and I'm going to explain how this can't be correct. So we have the elevation that Anderson gave us and the plan, okay? Now this can't be correct, and it's very simple to see why. If we treat this as a singly ruled surface, we'd be doing it like a regular orthographic view. We'd take this point here on our corner, bring it across to our end view, drop it down for our plan, and it would have been down here somewhere along the surface, joined back up. It would have been down at an angle along here, and we could have said then that was correct. However, it's not. So what we can say from this is that it's a hyperbolic paraboloid because we're given a surface stretched between two skew lines. Something else that Anderson could have made a mistake on in his book is there could actually be a fold line going from this point to this point, and he just mightn't have shown it. However, not showing that fold line is what's brought up this debate and this issue around this question. Is it correct? Is it incorrect? If the fold line is there, it is correct. However, the fold line isn't there, so we have to assume that it's incorrect for what we're showing. So what I'm going to do now is I'm going to show how this question cannot be treated as a single surface. And I've done that by drawing in our hyperbolic paraboloid. So what I've done is I've divided the surface into the sections that we use for hyperbolic paraboloid and joined the lines across. And as we rotate it to see this as what we would see as an edge view, we can see the curve. We can see our curve of the parabola. Yeah. Whereas if we were to look at two parallel lines, we'd be seeing them as an edge view. So if we were to look here at this line and this line, these lines are parallel. No matter what way we turn them, they're always seen as parallel. And as we bring them together, we can see that the lines appear to be one single line. Okay? Whereas here, our surface is warped and it's curved along a parabola. Okay, so now that we know that that question is wrong and that a hyperbolic paraboloid cannot be developed onto a flat surface, I've decided that I'm not going to dwell on that. And in developing my solution, I've decided that I'm going to use this as possibly a problem-based task in the future for students. So far throughout college, we've been say in pedagogy or in DCG, we've been told to focus on key principles, and then come up with ways of teaching that to students and giving them concrete, interactive, fun experiences where they can really learn something and hopefully remember what they're learning, not just put it into their short term, but put it into their long term memory. Something that that we've learned from education and just from ourselves, that we know that a real problem and solving a real problem can really help us do some real learning. It can bring our learning from our short-term memory into our long-term memory. So with that in mind, I've decided that I'm going to use this question as a problem-based task for students. So when I'm in class in the future, I'm going to teach structural forms. Then I'm going to come on to surface geometry, and depending on the ability of my class, I'll be able to then use this question as the problem-based task. So I'll be able to explain to them, okay, there's something wrong here with this question. Let's see if we can figure it out. And maybe we'll figure it out very simply by drawing an end view, bringing our point down and realizing, oh, that's not matching up. So what are we seeing here then? And continuing on then to explain to the students and hopefully teasing it out of them. Maybe they'll be able to tell us that that surface isn't a flat surface, that it's a hyperbolic paraboloid and it can't be developed onto a flat surface because it is a warped surface. So with the students, after learning that, we can go on and say, okay, so let's make a little bit of a case study out of this. We are a company and we specialize in transition pieces, and we need to make a transition piece to join these two pieces of ducting. Even though the solution in the book is incorrect, we still need to figure this out. So we're going to explain to the students, say that we're a company, we need to do it the cheapest way we can, the fastest way we can, and we got to be able to explain why it's going to work. Because say if we put this into a machine and we're going to make a one of these, it's going to cost thousands and thousands. We don't want to make it once thinking that it's going to work and not work. So they need to be able to rationalize why it's going to work, rationalize why they've chosen that particular style of a solution, and focus on key principles such as true lengths, rebatments, plane geometries, and any other aspects that they've learned throughout the core or from technology or from TG. So with that in mind, I'm going to go on now and start into how I feel the students might work with this. So to make it very interactive and kind of interesting for the students, we could start off by maybe putting them into groups, or start by developing a graphical organizer on the board, a bit of a mind map maybe with some sketches, and thinking what's going on here. Can we use triangulation? Should we be cutting along long lines or using fold lines? Should we fold along shortest lengths? What actually costs money in a company? Is it the people that are working? Is it our materials? How much material we use? How efficient we can be? The type of techniques we're going to use. Are some techniques more expensive or take longer to do than others? These are all things that we could use that we could use in our problem-based task, because it'd be giving the students a further understanding, and they'd actually maybe it'd sink in that this is something that's realistic and could happen in real life. So with that in mind, I've created a model of the actual transition piece that we're shown in Anderson's book, and this is actually what we're seeing. So we can see that the line of intersection between a transition piece and a rectangular ducting isn't going to be rectangular, because if we were to treat these as surfaces, which the question is asking us to do because it's asking us to develop the surfaces, they can't be a rectangle, because the line has to run along the surface because it's inclined. Whereas in the question given to us by Anderson, we can see that particular view is actually a rectangle. He's shown the line of intersection between the rectangular ducting and our transition piece as a rectangle, which we know can't be correct. So having worked this out with the students, we're going to let them work in their pairs to maybe figure out a solution. We could give them a piece of cardboard and let them draw out a few sketches on a page and cut out a few different models in cardboard and try fold them together and see how it might work for them, just to give them a bit more of a solid concrete experience. Sometimes when you're struggling with coming up with ideas and solving a problem, SolidWorks can actually slow you down and hinder you, and that's something that might not sound great because we want to use SolidWorks as a problem solving tool. However, if you're not very efficient on SolidWorks, it will start to slow down your thinking, and you'll actually start to try and do things in a way that you know you can do on SolidWorks. Whereas when you give a student a pencil and a piece of paper, they'll draw exactly how they think it's going to be done or how it's going to work, and then after that you give them the task of building it on SolidWorks, and that's where the learning can come into it as well. They're not just going to be learning about surface geometry, but they'll also be developing their ICT skills and their CAD skills. So from the sketches, I done a few sketches myself, and from my sketches I came up with two possible solutions for the ducting. First one, I decided to add on this piece to the top of my original transition piece. This is just a smaller piece added to my transition piece to join my rectangular ducting to the original transition piece. And what I've done here is I've actually used the line of intersection that we know is really there, and I've used triangulation to bring that back to our original rectangle, still at 45 degrees. So these lines here are parallel to each other, so both surfaces will be parallel. Okay, and I've used triangulation then to bring those back up to our ducting. And I'll show you then how this is assembled. So this is actually assembled just like so, and our rectangular ducting would slide into place here. So the rationale I give for this solution would be that we know that the bottom transition piece is going to work based on principles, and we know we can develop it out, because we can use rebatment and we can use triangulation to find true lengths, and so we can see all the true lengths that we need to find in that, and we know that's going to work. As well as that, working with a smaller piece of material that we're going to add on to the top here could be more efficient for us in the company. It'll cost us less to work on a smaller piece of material because any cuts we're going to make are shorter cuts. Any folds or any welds are shorter distances, so they take less time, which means we have to pay our employees for less amounts of time, saving us more money and in the end making us money. The key principles I've been looking at here on this one were triangulation, so I can take my points, 3 points, and I can find where they are. I can also use my center axis here to bring it up and find where my rectangular piece is intersecting, and I can draw in my real line of intersection between my new transition piece and my ducting, which is just here, which is going to be identical to that of the identical area of that of the ducting. Okay, so another solution that the students may come up with, and it's a solution that could have been staring us all in the face but we never really thought of, is that Anderson might have actually just forgotten this line here, the fold line. May have accidentally deleted it in his elevation and in his plan. Okay, so this fold line would turn our warped surface into two triangles, and the two triangles are on a plane surfaces, which means they can be developed. Okay, so we could have developed these two surfaces. However, now that I brought this into a problem-based task, I want the students not only to be able to tell me the principles of why this is going to work, but I want them to explain why they think that we should choose this over adding another piece onto the top of our main transition piece. So the students might say that it's the easiest to make because we only have one long weld to do, or something along those lines. Or they might try and say to us that it's forming the least resistance for whatever is going through the ducting, because it's still very similar to just the funnel, and it's less of a sharp bend, so there's less material to get caught or slowed down as it's going through, which are all valid points. However, at the end of the day, money is important, and it will take a company longer to either cut that line or fold that line or weld that line, because it is more material and it's further distance to go. And because of that, although this is correct, as a class we try and decide that we're going to stay away from this design and add on a smaller piece to the top of our ducting. This is just a model that I made to show the students our issue. I should have shown it earlier in the videos. Sorry about that, I mixed up where I was going. But we should have shown this earlier in the video, and it's to show what we were going to show the students to explain that there was an issue with our ductings. So this is our rectangular ducting that we were given, and we're told it's going to intersect with our transition piece. This is the transition piece that is drawn by Anderson, and as we treat this as a surface. So we can see here that this triangle here that's formed will actually be a gap. So we can explain to students, say if this was a duct and letting water down a chute for your gutter relating it to construction, or if it was an air vent, there'd be air coming out through this, maybe blowing dirty air back into a room if we're relating to the mechanical heat recovery system in construction. Or depending on where we are, we can relate this to farming. We could say if this was a feeder for an animal or something to catch for pellets or grain or something along those lines, comes some kind of a chute, that we'd be losing material out through these sides, and at the end, and that's going to cost us money, and it's not ideal. Out through this gap we'll be losing material. So that might just give them an incentive to try and solve the problem and explain, and it's very much the teacher's decision as to what they use to explain that. So if I was teaching in inner city Dublin, I definitely wouldn't relate this to a feeder on a farm, because they wouldn't have a clue. Whereas if I was teaching, I don't know, somewhere down the country, I'd definitely consider doing that, because it'd give them a connection to their life and something that they've actually seen and know, which could really make a big difference when it comes to trying to get them to trying to stimulate the students. So that's my critique of this question by Anderson and my solutions. I hope you like the way I decided not to dwell on the problem, and I decided to solve it and use it as something that could help me in the future. So I know now in the future when I'm teaching in a class, I'm going to do structural forms before I do surface geometry, and if my class are good enough, I can make a very, very good, very interactive task out of this question that will give the students the understanding that everybody makes mistakes, but a mistake can always be solved, and there's no point in dwelling on it, which can be a very valuable life lesson for students. Thank you very much.